While some publications are saying that AI scaling has hit a wall, there's a few recent developments that are saying that that's highly unlikely, including what I think can be referred to as Q-Star 2.0.
Get over here and hit like. This is no time to freeze.
So if you recall Q-Star, that leak back in 2023, that was the model that we know today as the O1, aka Strawberry, which is showing some great results. And by the way, shortly before recording this, a Chinese model, DeepSeek R1 Lite Preview, was released showing that it could be competitive with O1, meaning that within 1 or 2 months since the O1's release, Chinese researchers were able to kind of like break it down, reverse engineer it, and rebuild it. Now, it doesn't seem like it's quite as good. As you can see here on these charts, it beats the O1 preview in 1 or 2 and is slightly worse off on the rest of them. But notice that it's definitely going to give the O1 a run for its money. With enough time, it's likely that it's going to catch up. If you want to try it out for yourself, you can try it at chat.deepseek.com. But that's not even what we're talking about today, because there's yet another approach that's showing a lot of promise. That's this sort of idea of Q-Star 2.0 potentially, because it adds yet another level to this whole thing. This from a paper called The Surprising Effectiveness of Test Time Training for Abstract Reasoning from MIT. We'll get to that in just a second, but the big news here is that it did really well on the ARC-AGI, which some say is probably currently the only benchmark that's kind of worth pursuing that means anything. The reason being is because it's trying to test for actual AGI, artificial general intelligence, the ability to generalize and complete tasks it's never before seen. And that's the problem with a lot of these other benchmarks, because we're not sure if maybe the answers are part of the model's training data. Maybe it's just memorizing some things. All right, so really fast, let me just explain a couple of key concepts or key terms that are going to help you understand what the heck we're talking about. If you know all these, give yourself a pat on the back, but just really fast, let me quickly run through them. So first of all, imagine you have a dog and you're trying to have them run through those dog obstacle courses where they jump over things, go side to side, bob and weave through various obstacles. And in order to compete at the highest levels, you set up 5 of these little obstacle courses in your backyard, and you just keep having your dog run through them over and over and over again until it gets good at those courses. So the dog here is the AI model, right? So similar to how a dog has a neural net in its brain, a AI model is basically kind of a digital representation of that. So kind of similar. And the 5 training courses you set up in your backyard, or the little 5 training obstacle courses that you've set up, that's the training data. That's what you train the dog on. That's its kind of practice area. Now, do we care how good the dog gets at running those 5 obstacle courses? Well, not really. I mean, it's a good sign, certainly, but that's not the point for it to just memorize those 5 courses. We want it to be able to go to the competition, and whatever the judges and designers of this competition, whatever they throw at it, it should perform flawlessly. So the dog competition, that would be the test data. So in terms of the AI model, that's the test data that we will be testing on. So we have the training data and we have the test data. So the big point to understand here is while we're training the model, the dog, on these, courses that we have at home, that's the training data, we actually don't really care how well it performs on those 5 courses. We're trying to get it to be great at all the courses that it has never before seen. At the infinite variety of courses and obstacles that somebody can throw at it, we want it to sort of be able to do really, really well at those. That's called generalization. And the reason this is important is because, of course, we can create some algorithm or some robot or whatever that goes through these 5 courses where we know exactly what they look like, where everything is laid out and perfectly memorized, and we can have it just completed in record amount of time just by scripting certain movements. But that's not what we're going here. We're going for creating a neural network, a brain of a sort that's able to generalize and become good at all the stuff that it hasn't seen, to generalize. And overfitting, sometimes you'll hear this term, so that basically means that we've trained it so much on these 5 courses that it became really good at it, almost at the cost of being able to generalize, to be able to run the big doggy competition. This would be like memorizing the answers to the test. So, like 1 is A, 2 is B, etc. But if the test has any questions out of order or even slightly different, you're completely at a loss. That's overfitting. All right, so with that out of the way, here's the ARC prize. So they're saying AGI progress has stalled, new ideas are needed. And it's $1 million prize, it's a public competition to beat, and open source a solution to the ARC AGI benchmark. Here in blue, you kind of see these other AI benchmarks that we use, these other AI tests that we use to determine how good a particular AI model is. And as you'll notice, most of them blow past the human capability within, some under a year, some around 5 years. But the ArcAGI prize and the ArcAGI benchmark is different. As you can see, the models are still well below human capability. As they say here, ArcAGI remains impossible for AI. Here's the creator of this benchmark, Francois Chollet. He wrote this paper many moons ago on the measure of intelligence while working at Google back in 2019. Here's just a quick snippet of the problem as he sees it, the problem that he's trying to solve.
I had this sense that, sure, we were making progress on tasks, like we had solved Go. We are making very fast progress on image recognition problems, then on natural language processing problems. But I was feeling like the ultimate goal of the field of artificial intelligence, which is human level general artificial intelligence, was just as out of reach after all this progress as it was in the beginning. And so I was like, well, if all these data sets and benchmarks are not a good way to measure progress and to get a feedback signal, then what could be a better feedback signal? And if you want to answer this question rigorously, then you need to define what is intelligence. You need to define what it means to be intelligent. And that's where you start, acknowledging that task-specific skill is not a good proxy for intelligence. And the reason is simply that as soon as you fixed the task that you're interested in, it becomes possible to achieve arbitrary levels of skill without leveraging any intelligence, simply by bypassing the problem of intelligence and leveraging, for instance, so either a hard-coded solution to the problem that is produced by humans, like that's what you do with a chess engine, for instance. You have very smart people, human beings, think very hard about the problem, model it basically as a search space, then get a very fast computer to search through that search space, and then you get a system that is extremely skillful. It is in fact superhuman at chess, but it can only do chess. It's not intelligent in any real sense. And the other way you can cheat is by simply training on so much data that any situation you see at test time is a very simple variation on what you've seen at training time. And again, in this situation, you don't need intelligence, you just need a memory and the ability to generalize just a little bit away from what you've memorized.
So you can look at some of these models out of Google DeepMind, whether it's playing Go or chess or predicting the structure of the proteins. I think it's fair to say that that is artificial super intelligence, in a sense that it's far superior to any human. No human can beat it at Go or chess or whatnot, but it's narrow. It's not general intelligence. AlphaGo can't really do anything else other than just crush you at that game. So all those models, while useful, while very cool, while very impressive, you kind of have to agree they don't really fall under that category of general intelligence. Meanwhile, with the large language models, etc., they get trained on so much data, both real, human-made, and synthetic, that at some point you got to ask yourself, well, what part of the test data is in its sort of training data? Right. So in our example with the dog, right, if you were able to, get pictures of the dog competition obstacle course and perfectly recreate it in your backyard and just have your dog run those courses or run that one course, certainly it would get really good at that course. But again, that's not really showing generalization. It's not generally good at any and all courses that can possibly be created. And so the ArcAGI, you can think of this as the training data, right? So this is not for the models. This is more for us humans to kind of look at and figure out if we can actually solve it, right? So you look at the example inputs and outputs and you see if you can spot a pattern. This might be fairly straightforward. The second one may be a little bit different, but certainly still not super complex. Basically different colors here correspond to different sort of position of other colors around them. And in the case of this light blue one, nothing happens. And by the time you get to the last example, well, it gets a little tricky. And the goal here is to do something that's easy for humans. So if you have general intelligence, just like a human being, you should be able to figure this stuff out. But it should be very difficult for AI. So if all of us take this test and we get a certain percentage, and we'll call that like the human baseline, the human sort of level of ability on this test, then no currently available model, AI model, would be able to beat it. And so here they've set sort of that threshold at 85%. There were some people that sort of like pointed out that the actual sort of human baseline, human level is a little bit lower. 85%, we'll set that as like the level. If they get over that, then they will get the ARC prize. And so currently these are the high scores, the leaderboard for the sort of the public ARC AGI. And you can see those submissions, the competition notebook on Kaggle.com. Kaggle.com is, of course, this large AI and machine learning community, tons of data sets, lots of competitions. And of course, one of the competitions is the ARC AGI. So as you can see here, we're still quite a ways away from 85%, which brings us back to that paper out of MIT, the surprising effectiveness of test time training for abstract reasoning. And so really fast. So we used to train models like GPT-4, for example. We would train it and then we would run inference. We would ask it questions. So there would be a period of training, and then it would be ready to answer our questions. This model would be rather static, and it would kind of spit out answers immediately. Next, we have the O1 model, and that was a little bit different because here is where OpenAI introduced us to this idea of test time compute, basically allowing the model to think through the answer and use more of the computational resources to think about the problem before answering. Which, by the way, that model, the Chinese model, DeepSeek, it seems to be they cracked the code on how to do that. As you can see here, it improves accuracy with test time compute scaling. So as you can see here, as the average number of thought tokens per problem, as it goes up, as we give it more time to think and talk its way through the answer, the accuracy keeps increasing. So they kind of like cracked that approach that OpenAI, they were the first ones to kind of introduce this to the world. Again, so that's the O1 model, the test time compute, and that's also the same thing that it looks like this DeepSeek model is doing. But this new thing, it's something new entirely. It's called test time training. So just keep that in mind. Test time training, TTT, versus test time compute, TTC. This is kind of the OG model, if you will, the original, right? This one was the one that was referred to as Q star, aka Strawberry. And this is the Q star 2.0, if you will. That's not the official term, but it does seem appropriate. So they begin by stating the problem pretty well, I think. Language models have shown impressive performance on tasks within their training distribution, right? So if they got trained on that obstacle course, they know how to do that obstacle course. But they often struggle with novel problems requiring complex reasoning. Again, if it's a trick question, they haven't seen those types of trick questions before, they're going to fail at it, most likely. The novel, the never before seen problems they struggle with. And so these people out of MIT, they investigate the effectiveness of test time training, updating model parameters temporarily during inference using a loss derived from input data. And interestingly, I think Mark Zuckerberg in the interview with Dwarkesh Patel did kind of hint at this a while back, saying that there's more of a blurring of a line between training and inference. So training is when we feed it the data. Inference is when we ask it the questions, so kind of input, output. But here you can almost say it's kind of getting trained while we're asking it to answer the questions. And so this idea, they're using this mechanism for improving the model's reasoning capabilities using the abstraction and reasoning corpus ARC. That's what it stands for. So the ARC AGI, and they're using that as a benchmark. And test time training significantly improves performance on ARC tasks, achieving up to a 6 times improvement in accuracy compared to base fine-tuned models. So they've used this TTT to a 8 billion parameter language model. So rather small, and they're achieving a 53% accuracy on the ARC's public validation set. And by assembling our method with recent program generation approaches, they get the state-of-the-art public validation accuracy of 61.9%, which is matching the average human score. So again, the threshold for the ARC AGI is 85. There was a paper we looked at last time. We didn't read the whole thing, but they were saying, the sort of the average human score, it was somewhere in the 60s, I believe. I don't remember the exact number. But here they're saying, so they've matched the average human score by using this sort of approach. And this test time training, it's important to understand that it operates in an extremely low data regime. Whereas the initial training might be massive amounts of data, this is very, very small amounts of data that it's getting kind of like continuously trained on. And so they're mentioning that the ARC corpus, right, abstraction reasoning corpus, is an ideal benchmark for testing the limits of language models, their generalization ability, right? So the ability to kind of generalize to novel, never before seen tasks. And they note how current language models do perform poorly on the ARC currently. So how exactly is it doing all this magical stuff? Well, So test time training, TTT, this technique that we're talking about, enables parametric models to adapt during inference through dynamic parameter updates, an approach that remains relatively unexplored in the era of large language models. So it's adapting its sort of parameters, how a brain works, if you will, during the questions that it gets during inference. So as we're asking it questions from the test, it rapidly kind of trains itself up to be better able to answer that test question. So the model leverages the test data itself to improve its predictions. So the general TTT process works as follows. Starting with the initial model parameters, right? So basically it starts with its initial parameters like it was trained for, right? Static. For each test input or batch of inputs, so you can think of this as the test questions, like if you're answering a test, so it's any one of the questions, or batch of inputs where that's like the whole test or number of tests. We first generalize the training data from the test inputs. So that might be a little bit hard to grok, but the thing that really makes it clear for me, I actually got to say thank you to Google DeepMind, this blog post they made. They had alpha geometry and alpha proof in the combination of two AI models. They actually got close to a gold medal in the IMO, the International Mathematic Olympiad, which was kind of a big deal. And here they kind of explain in part how they did it. But one of the things that kind of jumped out at me is this: generating 100 million synthetic data examples. So this is, of course, going to be a little bit different from what they're talking about in the TTT paper, but I think this really kind of helps grasp the concept. So here they're talking about the synthetic data generation approach that emulates kind of the human knowledge building process, but at scale, which allows them to train alpha geometry from scratch without any human demonstrations. So this system starts by generating 1 billion random diagrams of geometric objects and relationships between the points and the lines in each diagram. Alpha geometry found all the proofs contained in each diagram, then worked backwards to find out what additional constructs, if any, were needed to arrive at those proofs. We call this process symbolic deduction and traceback. So it was kind of a brute force approach, went through and created 1 billion of these like examples, basically random diagrams, got the proofs for them, right? Then they took out various ones that were too similar. So that left them with a data set of 100 million unique examples of varying difficulty of proofs, right? How to do proofs, right? The point is it kind of like dreamed up its own training examples, this synthetic data, and then it got trained on it. And then it was good at proofs. Another example with the dog and the obstacle courses, it's like having the dogs themselves build a bunch of obstacle courses and then just run it until they figure it out. So when they're saying here this is back to the TTT, they're saying we first generate training data from the test inputs. So it's somewhat similar in that they're looking at the test questions and answers, and they're sort of using that to create synthetic data to kind of test itself on. So if you ever had an important test and maybe you created little quizzes for yourself that you had to go through and answer to make sure you kind of knew what you were doing, you wrote out your own kind of like fake synthetic test questions and then quizzed yourself on them. This I think is kind of similar. And they're saying then we optimize these parameters to minimize loss function, producing temporarily updated parameters for prediction. So this is where they're actually like changing sort of like the neural network, the brain, to be better able to answer those specific batch of questions, that question or those batch of questions. And then after generating predictions, this is kind of interesting, the model is restored to the original parameters that it started with before that test question came in for the next instance or batch. Thus, TTT trains a specialized prediction model for each test input obtained by fine-tuning a base model on a test time dataset generated from that test input. It's kind of interesting to think about that the fact that like the act of us testing it and asking it questions makes it teach itself almost to be better at answering those questions. So with that, let me ask you a couple of questions here. Number one is, do you think that scaling has hit a wall? Are we about to see an AI winter of sorts where just our ability to keep improving these models is just going to hit a wall or a plateau of some sort? Is it going to drastically slow down? Again, we have like the O1 model, we used to be called Q star, right? So it rolls out. A few months later, there's a Chinese version of it that seems to really have figured out how they're doing it. Maybe you can say it's not quite as good, but it's going to catch up. And it sounds like it's going to be open source. So that's open source Q star that's going to be available pretty soon by the sound of it. This should be huge news, but at the same time, it's kind of overshadowed potentially by this new approach, this test time training. That's taking a small model, this 8 billion parameter model, that gets 61% on the ARC AGI. It sounds like we might hit the 85% benchmark for winning that prize pretty soon. So the competition for this year, so people have submitted everything and there's a verification in progress. And so the winners are going to be announced on December 6th. By the way, we looked at this last time. So somebody's saying scaling has hit a wall, and that was a 100% eval saturation. So basically that idea that, for a lot of these benchmarks, as we approach 100%, it's kind of hard to see how much the models are improving. We're getting as close to the edge as possible. David S. Holtz replies, what about Chollet's ARC eval? So this is the ARC AGI that we're talking about. And Mr. Sam Altman himself jumps in and goes, in your heart, do you believe we've solved that one or no? Right. So in other words, if the MIT paper takes an 8 billion parameter model, trains it with this test time compute technique and gets, 61.9% on the ARC eval, could an outfit like OpenAI crack 85%? Now, they're probably not going to follow the rules of the competition because you have to open source the model. There's a lot of stuff you have to reveal about the weights and stuff like that to make sure that it's sort of no one's cheating. So I'm not saying they're going to enter the competition, but I'm asking is do you think they have the capability to crack the 85% on there? Certainly, this seems like it's implying that Sam Altman's saying yeah, we did it. We cracked it. But will we beat the ARC AGI prize? Does OpenAI already have AGI up their sleeve? All that and more coming up on your favorite AI channel. My name is Wes Roth, and I'll see you next time.